A cosmic city is about to be torn apart. Not a city of buildings, but a metropolis of 1,000 galaxies, each containing billions of stars. This is a galaxy cluster, the largest structure gravity can hold together. And when two of these titans collide, it unleashes the most violent event since the birth of the universe itself. By the end of this journey, you will hold 30 astonishing secrets about these cosmic smash-ups, from how they prove the existence of invisible dark matter to how they forge the very elements of life. How can a collision last for billions of years? What ghostly substance passes through the wreckage untouched? What sound does a supercluster make? The answers will redefine your sense of scale. What do you believe is the most powerful force in the cosmos? This cosmic city is defined by its sheer scale and complexity. A single galaxy cluster is not just a random scattering of galaxies. It is a true metropolis of the universe, bound together in the unbreakable grip of gravity. Within its borders, you will find hundreds, sometimes thousands, of individual galaxies, each a swirling island of billions of stars. But the galaxies are just the visible skyscrapers. The true bulk of the cluster is an immense, seething ocean of superheated gas, so hot it glows in X-rays, filling the space between galaxies, and woven through it all, providing the gravitational anchor for this entire structure, is an invisible, mysterious substance we call dark matter. This trifecta, galaxies, hot gas, and dark matter, makes a galaxy cluster the single largest gravitationally bound structure we know of. To put its size in perspective, our own Milky Way is part of a much smaller gathering called the Local Group, which has only a few dozen galaxies. A full-fledged cluster makes our neighborhood look like a quiet village compared to a sprawling, luminous megacity. And when two of these megacities are pulled together by their mutual gravity and finally collide, the result is catastrophic. It is not simply two galaxies bumping into one another. It is the collision of two entire ecosystems. Hundreds of galaxies from each cluster intermingle, their stars almost never touching due to the vast distances between them. Meanwhile, the colossal clouds of multimillion-degree gas from each metropolis slam together at speeds of millions of miles per hour, creating shockwaves of unimaginable energy. And the dark matter, the unseen scaffolding of it all, does something even stranger. It begins a ghostly dance through the wreckage, a clue that will soon become central to our entire investigation. The timescale of these events is almost impossible for the human mind to grasp. We see the word collision and think of a split-second impact, a flash of destruction. But in the cosmic arena, a collision is a ballet performed in agonizingly slow motion, a single dance that can last longer than our planet has existed. This gravitational tango unfolds across billions of years, a process so gradual that from our fleeting vantage point, every cluster collision we observe is merely a single, frozen frame in an epic film. The dance begins with two clusters, separated by millions of light years, feeling each other's gravitational pull. They start their long, slow fall toward one another. The first close pass is not a head-on crash, but a swing by, where their cores may brush past each other. This initial interaction stretches and distorts the clusters, intertwining their galaxies like two crowds passing through one another. Then, slowed by their own immense gravity, they fall back together for a second, closer encounter, and a third, each pass drawing them tighter until they finally merge into a single, chaotic, roiling entity. Even then, the process is not over. It takes billions more years for this new, combined cluster to settle down, to relax into a stable, spherical shape. A perfect example is the famous bullet cluster, which astronomers have identified not as a finished merger, but as two clusters caught in the act of a recent, high-speed pass-through. We are seeing just one moment, perhaps a few 100 million years after their closest approach, in a sequence that will continue for eons to come. This timescale means that to understand the full story, astronomers must be cosmic detectives, piecing together the narrative from snapshots of different collisions, each frozen at a different stage of the same unimaginably long dance. While the galaxies glide past each other like phantom ships, the true spectacle of destruction belongs to the sea they float upon. This is the intracluster medium, a superheated ocean of plasma that fills the vast emptiness between the galaxies. In a single cluster, this gas is unimaginably hot, often reaching tens of millions of degrees. But when two clusters collide, this is where the most violent, visible drama unfolds. The gas from each metropolis does not pass through the other peacefully. It slams together at a significant fraction of the speed of light. Think of two tsunamis, each made of a seething, multimillion-degree plasma, crashing head-on. The collision creates titanic shock waves, rippling through the gas like sonic booms on a cosmic scale. The friction and compression from this impact heat the gas even further, to temperatures soaring past 100 million degrees. At these extremes, the gas does something extraordinary. It glows not in visible light, but in a fierce, high-energy radiation called X-rays. This is the primary way we see these cosmic collisions. Space telescopes like Chandra are our X-ray eyes on the universe, and what they reveal is breathtaking. They show us the aftermath not as a simple blur, but as intricate, sculpted structures. We see vast, curved shock fronts like the bow waves of a cosmic ship, and turbulent, swirling eddies of plasma. In the bullet cluster, the image is unmistakable. A bullet-shaped cloud of gas, the remnant of one cluster's core, has been punched right through the heart of the other, leaving a wake of shocked, glowing material behind it. This luminous wreckage tells us exactly where the forces of the impact were most intense, painting a vivid picture of violence on a scale that defies belief. Yet amidst this plasma inferno, the galaxies themselves behave in a way that seems utterly bizarre. They pass through the chaos like ghosts, in a collision that unleashes energies capable of reshaping the cosmos. The galaxies, the very cities of stars we think of as solid objects, are almost entirely unaffected. This is because a galaxy is not a solid thing. It is overwhelmingly, incomprehensibly empty space. If you could shrink our sun down to the size of a grain of sand, the next nearest star would be another grain of sand over 4 miles away. Now imagine two swarms of bees, each containing thousands of individuals, flying through each other at high speed. The chances of any two bees actually colliding are vanishingly small. This is exactly what happens when two galaxy clusters merge. The hundreds of galaxies from each cluster intermingle, their orbits stretched and twisted by the changing gravity, but the stars within them almost never touch. They sail right past one another, their vast separations acting as a perfect safety buffer. This creates a profound separation in the aftermath. The superheated gas, which is collisional, gets stuck in the middle of the impact, slowed down and heated to extreme temperatures. But the galaxies, along with the mysterious dark matter, are collisionless. They simply keep moving, passing through the wreckage of the gas and emerging on the other side. This ghostly behavior is not a minor detail. It is the key that allowed astronomers to make one of the most important discoveries of the 21st century, a discovery that hinges on seeing what is not there. This ghostly separation of the galaxies was the first clue, but the real proof came from mapping something we cannot see at all. Colliding galaxy clusters are not just cosmic disasters, they are perfect natural laboratories for uncovering the secrets of dark matter. To solve this mystery, astronomers had to become cosmic cartographers, creating two different maps of the same catastrophic event. The first map uses X-ray telescopes to chart the superheated gas, the normal matter that slams together and glows so brightly. This gas, being made of particles, experiences friction and gets slowed down and stuck in the middle of the collision. The second map uses a phenomenon called gravitational lensing. This is where the immense gravity of the cluster, from all its mass, warps the fabric of space-time itself, bending and distorting the light from galaxies far behind it. By carefully measuring these distortions, astronomers can create a precise map of where all the mass in the cluster is located, the total gravitational footprint. When scientists compared these two maps for the bullet cluster, the result was earth-shattering. The map of the hot gas showed a bright, messy cloud right at the center of the impact. But the gravitational lensing map, the map of where the actual mass was, showed two distinct, massive blobs. These heavy concentrations of mass were not aligned with the gas. They had sailed right through the collision, just like the galaxies, and were now positioned on either side of the gaseous wreckage. This was the definitive evidence. The majority of the mass in the universe is not in the stars or the glowing gas. It is in this invisible, collisionless substance that feels gravity, but does not interact with light or with itself. Dark matter is real, and in a cluster collision, its ghostly nature is written across the sky for us to decode. The most famous of these cosmic collisions bears a name that perfectly captures its violent nature. It is officially catalogued as 1E0657-56, but we know it as the Bullet Cluster. In the deep southern sky, this system is a forensic snapshot of a high-speed impact, a moment frozen in time that forever changed our understanding of the universe's composition. The iconic image is unmistakable: a dense, bullet-shaped cloud of pink, representing superheated gas, appears to have been shot clean through the heart of a larger, more diffuse cloud. This is the visual signature of a smaller, dense cluster that has plowed at immense speed directly into a larger, more massive one. The bullet shape itself is a colossal shock wave, a sonic boom rippling through the plasma at millions of miles per hour, heating it to such extremes that it glows fiercely in X-rays. For years, this image alone was a stunning demonstration of cosmic violence, but its true, revolutionary significance lay in what happened when astronomers looked beyond the hot gas. They mapped the total mass using gravitational lensing, creating a picture of where the gravity was strongest. That map revealed two heavy, invisible clumps of mass that did not align with the pink gas at all. These gravitational anchors were positioned on either side of the gaseous wreckage, precisely where the galaxies of each cluster had sailed through. This was the smoking gun. Here was direct, empirical proof that most of the mass in the universe was not in the visible, colliding gas. It was in something invisible and collisionless that had traveled right alongside the galaxies. The bullet cluster did not just suggest dark matter existed. It showed us its ghostly behavior in action, separating from normal matter as cleanly as oil separates from water in a jar. This single observation moved dark matter from a compelling theory to an observed, physical reality, forever cementing this collision's place as one of the most important astronomical discoveries of our time. This violent stripping has a name: Ram pressure stripping, and it is one of the most transformative forces a galaxy can endure. To understand it, picture a galaxy not as a static island, but as a ship sailing at incredible speed through a dense, invisible atmosphere. During a cluster collision, the space between galaxies is flooded with that superheated, high-pressure plasma we call the intracluster medium. When a galaxy, particularly a spiral rich in cool gas clouds, plows through this dense environment, it experiences a relentless, cosmic headwind. The pressure from this impacting gas is so immense it acts like a hurricane-force gale, but one made of multimillion-degree particles. It does not gently push, it violently scours. It seizes the galaxy's own reservoir of cool, star-forming gas and rips it away, leaving behind a ghostly tail of stolen material that can stretch for hundreds of thousands of light years. Astronomers can actually see these tails in observations, luminous streamers of gas being torn from their galactic homes. The consequence is profound and permanent. That cool gas was the galaxy's future. It was the raw fuel needed to birth new generations of stars. With it gone, star formation grinds to a halt. The galaxy's vibrant, blue, spiral arms, fed by ongoing stellar births, begin to fade. Over time, the remaining stars age together, their collective light shifting toward redder hues. The galaxy transforms from a blue, star-forming spiral into a red, quiescent elliptical, a cosmic retirement home for aging stars. In the aftermath of a cluster collision, ram pressure stripping is the quiet assassin, not destroying galaxies in a flash, but slowly and systematically starving them of their potential, turning vibrant cities of creation into silent, red monuments of what once was. Yet this cosmic violence has a dual nature, a creative power hidden within its destructive force. While the great headwind of ram pressure can starve a galaxy, the very same collision can also trigger a spectacular, if brief, renaissance of creation. The key lies in the shock waves themselves. Those titanic sonic booms rippling through the gas do not just heat it, they also create regions of immense, crushing pressure. Imagine a vast, cosmic hand suddenly squeezing a cloud of cold molecular gas drifting within a galaxy. Under this sudden, violent compression, the delicate balance within the cloud is shattered. Gravity, always waiting in the wings, gains the upper hand. Dense knots within the cloud collapse under their own weight, their cores heating up until nuclear fusion ignites and a new star is born. In the chaotic environment of a merging cluster, this process does not happen in a slow, steady trickle. It can explode into what astronomers call a starburst, a frenzied episode of star formation. A galaxy caught in the right part of the collision may begin forging new stars at a rate hundreds, even 1,000 times faster than our own peaceful Milky Way. For a short, brilliant period, the galaxy becomes a dazzling fireworks display of stellar birth, lighting up with the blue-white glow of massive, young stars. This is the universe's ultimate paradox, using the shock of a catastrophic impact to seed new suns. But like any brilliant firework, it cannot last. The starburst consumes its fuel with reckless speed, depleting the galaxy's gas reserves in a mere tens of millions of years, a blink in cosmic time. Often, this creative burst is just a prelude to the starvation we discussed earlier, a final, glorious blaze of glory before the galaxy's star-forming days are ended for good. These shock waves do more than sculpt gas and trigger starbursts. They forge the universe's most powerful natural weapons. Deep within the turbulent aftermath of a cluster collision, the immense shock fronts act as cosmic slingshots of unimaginable scale. They capture charged particles, like protons and electrons, that are swirling in the magnetic fields lace through the hot plasma. As these particles bounce back and forth across the shock wave, trapped by magnetic turbulence, they gain a tremendous burst of energy with each crossing. Over time, this process accelerates them to velocities approaching the very speed of light. We are talking about individual subatomic particles being hurled across space with energies millions of times greater than anything produced in our most advanced particle colliders on Earth. These are cosmic rays. An emerging galaxy cluster is their ultimate factory, but we cannot see these particles directly. Instead, they announce their presence through a ghostly radio whisper. When these ultra-relativistic electrons spiral along magnetic field lines, they emit a faint but broad signal in radio wavelengths. Our radio telescopes on Earth pick this up, revealing colossal, ethereal structures that cloak the entire collision site. Astronomers call them radio halos and radio relics. A radio halo is a vast, diffuse cloud of radio emission that seems to fill the central region of a merging cluster, a signature of turbulence and acceleration throughout the wreckage. A radio relic is even more dramatic. These are often giant, arc-shaped structures found on the outskirts of the collision, tracing the location of the most powerful shock waves, like the glowing aftermath of a titanic explosion. These radio ghosts are the direct fingerprints of the universe's own particle accelerator at work, a machine of such staggering power that it dwarfs all of human engineering, operating silently in the dark between the galaxies. These colossal arcs of radio light are not just random features, they are the literal outlines of the explosion. A radio relic is the glowing, million-light, year-long signature of a single, titanic shock wave that has traveled out from the heart of the collision. Think of it like this. When a bomb detonates on Earth, the initial fireball is followed by a powerful shock front that races outwards, compressing and heating the air as it goes. In a cluster merger, the initial impact creates a similar, unimaginably vast shock wave that propagates outwards through the thin, magnetized plasma at the edges of the cluster. As this shock front travels, it acts like a cosmic particle accelerator, sweeping up electrons and flinging them to near light speeds. These ultra-energetic electrons then spiral along the magnetic field lines frozen into the plasma, and in doing so, they emit that faint, telltale radio whisper we can detect. What makes a relic so distinct from a radio halo is its shape and location. While a halo is a diffuse cloud of turbulence in the central wreckage, a relic is often a sharp, thin, and beautifully curved arc, found far from the cluster's core, precisely tracing the outer boundary where that single, immense shock wave is currently traveling. Some of the most stunning relics look like celestial bow shocks, as if the entire cluster is a ship plowing through the intergalactic medium at supersonic speed. Their sheer scale is a direct measurement of the merger's power. A single relic can stretch for 5 or 6 million light-years, a distance that would take you from our Milky Way to the Andromeda Galaxy and back again, more than 10 times over. That is the size of the echo from a single cosmic detonation, a fossilized sound wave from the most powerful event in the modern universe. The sheer gravitational chaos of a cluster merger can fling entire galaxies into the abyss. While most galaxies are simply stirred into a new, blended orbit, the complex three-body gravitational interactions during the close passes can act like a cosmic catapult. Picture the core regions of two merging clusters swinging past each other, their immense gravitational fields whipping the surrounding galaxies around like stones in a sling. For a few unlucky or lucky galaxies, depending on your perspective, the timing and angle are just right to receive an immense, accelerating kick. This gravitational slingshot can impart so much velocity that the galaxy achieves escape velocity for the entire cluster. It breaks free from the gravitational grip of that cosmic metropolis entirely. Suddenly, it is no longer a citizen of any cluster. It becomes a rogue, a solitary wanderer hurtling through the immense, dark voids that separate the great filamentary walls of the cosmic web. These are intercluster galaxies, and their existence is a direct prediction of merger physics that astronomers are now beginning to confirm. They travel at astonishing speeds, millions of miles per hour, through regions of space so empty that the nearest major galaxy might be millions of light years away. Their fate is one of profound isolation, destined to drift for eternity in the cosmic deep, their satellite galaxies stripped away, their gas reservoirs slowly depleted. This violent ejection is a reminder that the aftermath of a collision reshapes more than just the central wreckage. It can send splinters flying out into the darkness, permanently altering the population of the universe on the largest scales. At the heart of a mature galaxy cluster lies a strange and paradoxical engine. This is the core, often dominated by a single, monstrous entity known as the brightest cluster galaxy, a behemoth that has grown fat by cannibalizing its neighbors. Surrounding this galactic titan is the densest, hottest part of the intracluster medium, a cloud of gas so thick with particles that it should be radiating away its colossal heat at a tremendous rate. According to all the simple physics, this central gas should cool down. As it cools, it should condense and flow inward in a river of plasma toward the cluster's center, a phenomenon astronomers call a cooling flow. This inward torrent should fuel an epic burst of star formation, turning the central galaxy into a furnace of new suns. But when we look, that is not what we usually see. The predicted deluge of new stars is missing. The gas remains hot. So what is stopping it? The answer lies with a dormant monster at the very center of the brightest cluster galaxy, its supermassive black hole. This black hole is not always quiet. As tiny amounts of gas finally do trickle in, the black hole awakens, feasting on this material, but it is a messy eater. In the process, it unleashes twin, focused beams of energy and matter that scream outward at nearly the speed of light. These are relativistic jets, and they punch far out into the surrounding hot gas, inflating gigantic bubbles and pumping tremendous heat back into the core. This is a cosmic feedback loop. The gas tries to cool and flow in, which wakes the black hole, whose jets then heat the gas back up, shutting off its own fuel supply. It is a breathtakingly precise balancing act, a battle between heating and cooling that has raged for billions of years. Then, a major cluster merger arrives. This catastrophic event is like throwing a boulder into a delicately balanced scale. The immense gravitational turbulence can violently stir the core gas, disrupting the steady trickle, feeding the black hole, and temporarily quenching its activity. Or it can have the opposite effect, funneling vast new reservoirs of gas toward the center, causing the black hole to erupt in an outburst of unprecedented violence. A single collision can reset this entire central engine, deciding the fate of the core for eons to come. The universe is not silent. It is filled with a note too deep for human ears to hear. In the heart of the Perseus cluster, a vast ocean of superheated gas is not still. It is ringing, like a bell struck long ago. This sound does not travel through air, of course, but through the seething plasma that fills the space between galaxies. Astronomers studying the X-ray glow of this gas discovered something astonishing. Rippling outward from the central galaxy were immense, concentric pressure waves, like the circular ripples from a stone dropped into a pond, but on a cosmic scale. These are true sound waves, propagating through the hot, thin medium. When scientists calculated the wavelength of these waves, the distance between one peak of pressure and the next, they could translate it into a musical note. That note is a B-flat, but this is no ordinary B-flat. It is a note 57 octaves below middle C on a piano. To put that in perspective, a single octave down doubles the wavelength. 57 octaves down means the wavelength of this cosmic sound is unimaginably long. The distance between one wave crest and the next is about 35,000 light-years. It takes the wave tens of millions of years to complete a single, slow oscillation. This is not a sound you could ever hear, even if you were floating in the middle of it. The frequency is far, far below the range of human hearing, but it is sound nonetheless, a deep, fundamental hum resonating through a volume of space millions of light-years across. That hum is likely the lingering echo of a past merger or the rhythmic pulsing of the central black hole, a continuous input of energy that keeps the cluster's gas from cooling too quickly. This single, profound note represents a staggering transfer of power, a low-frequency engine thrumming away in the dark, conducting the slow-motion symphony of the cosmos. These cosmic collisions are more than isolated events. They are brilliant flares that illuminate the hidden architecture of the entire cosmos. Galaxy clusters do not exist in lonely isolation. They are the dense, glittering knots tied at the intersections of something far greater, the cosmic web. Picture the universe's large-scale structure as a vast, three-dimensional spider's web, with threads of dark matter and gas stretching across the unimaginable voids. Where these filaments cross, gravity pulls matter into the dense nodes we see as galaxy clusters. When two clusters begin their fatal dance toward one another, they are not moving through empty space. They are sliding along these invisible filaments, following the dark matter highways of the web. Their immense gravitational pull acts like a cosmic vacuum, drawing in even more gas and galaxies from the connecting threads, funneling matter into the collision zone. This gives astronomers a powerful tool. By carefully studying the geometry of a merger, the direction from which the clusters approached, and the distribution of gas and galaxies in the aftermath, they can trace the lines of the filament that fed them. It is like seeing two rivers converge and, from the angle of their meeting and the sediment they carry, deducing the layout of the entire watershed that feeds them. In this way, a violent cluster collision becomes a probe, a flash of lightning in the cosmic dark that momentarily reveals the grand, filamentary skeleton upon which all visible structure is draped. We use the brightest, most energetic events in the universe to map its darkest, most invisible framework. This deep hum from the Perseus cluster is a constant reminder that the cosmos is dynamic, a universe in motion on the grandest scale. That motion extends far beyond the collisions themselves, to the very expansion of space, and here, in the violent wreckage of merging clusters, astronomers have found a surprising new tool to measure that expansion. It is a tool born of chaos, a cosmic ruler forged in fire. We have heard of standard candles, like certain supernovae, used to gauge cosmic distances. But merging clusters offer something different, something we might call a standard siren. The concept is brilliant in its simplicity. When two massive clusters collide, the event is not random. The dynamics, the speed of the impact, the distribution of the hot gas and the dark matter all follow the laws of physics and gravity. By creating incredibly detailed computer simulations and comparing them to our real-world observations of a collision. Astronomers can essentially reverse engineer the event. They can determine the cluster's masses and, crucially, their physical size. Think of it like watching a car crash in slow motion from a distance. If you know the make and model of the cars, you can calculate their speed and the force of the impact. But to know how far away the crash really is, you need a reference for their true size. In a cluster merger, the X-ray and gravitational lensing maps give us that reference. They tell us the actual, physical scale of the structures we are seeing, the true width of that shock wave, or the separation between the dark matter clumps. Once we know the true physical size, we can compare it to how large or small it appears in our telescopes. That apparent size gives us the distance, a direct measurement of how far away the collision is happening. This distance is completely independent of the traditional cosmic distance ladder. Now, combine this with another measurement, the cluster's redshift, which tells us how fast the universe's expansion is carrying it away from us. By comparing the distance from the standard siren method with the velocity from the redshift, you get a direct measurement of the Hubble constant, the rate of the universe's expansion. Each major merger becomes a single, powerful data point in the great cosmic debate, and the answers it is giving are deepening one of the biggest mysteries in modern cosmology, the Hubble tension. Measurements from the early universe, like the cosmic microwave background, suggest one rate of expansion. Measurements from the local universe, like supernova, and now these standard sirens, consistently suggest a faster rate. Merging clusters are adding their powerful, independent voice to this chorus, confirming that the discrepancy is real. This means our understanding of dark energy, the force driving the acceleration, or perhaps the very fabric of spacetime itself, might be incomplete. A violent event that tears cosmic cities apart is now helping us measure the very stretching of the space between them. 100 million degrees is not just a number, it is a state of existence beyond terrestrial comprehension. This is the staggering temperature reached by the intracluster gas during the peak of a major merger, a heat so ferocious it redefines the meaning of hot. To anchor this in something familiar, consider the heart of our own sun, the engine of our solar system. Its core burns at a formidable 15 million degrees Celsius, a temperature sustained by the relentless crush of gravity and ongoing nuclear fusion. The gas in a colliding cluster soars past that benchmark nearly 7 times over. We are talking about a plasma heated to 100 million degrees or more, an environment where atoms are not merely ionized, they are utterly shredded. Electrons are ripped from their nuclei with such violence that the gas becomes a seething soup of bare atomic cores and free particles, all moving at a significant fraction of the speed of light. This extreme heat is not a side effect, it is the direct, physical signature of the collision's raw power. All that kinetic energy from two clusters slamming together at millions of miles per hour has to go somewhere. It is converted, through immense shock waves and friction, directly into thermal energy, heating the gas to these astronomical temperatures. This is why we cannot see these collisions with ordinary optical telescopes. An object this hot does not glow in visible light. It radiates its energy in a much higher, more penetrating form of light, X-rays. Each particle in that superheated soup is moving so fast that when it collides with another, even in the thin plasma, it emits a high-energy photon. This creates a brilliant, diffuse X-ray glow that bathes the entire collision site. To study this furious aftermath, we must look with X-ray eyes. Space telescopes like Chandra, XMM Newton, and now eROSITA are our windows into this inferno. They translate those invisible, high-energy photons into the stunning, detailed maps we see, painting the arcs of shock waves and the turbulent cores in false color. That iconic pink hue in images of the bullet cluster or the coma cluster is not artistic license. It is a direct translation of temperature, a visual code for a violence that occurs at an energy scale where the very rules of matter are rewritten. The superheated gas of a cluster is far from empty. It is a rich chemical soup. This plasma holds the story of cosmic creation, a record of every star that has ever lived and died within the cluster's borders. Those stars are the universe's alchemists. Deep in their cores, through nuclear fusion, they forge simple hydrogen and helium into heavier elements like carbon, oxygen, and iron. When massive stars reach the end of their lives, they explode as supernova, an even more violent forge that creates the heaviest elements in the periodic table, from gold to uranium. For billions of years, these newly minted elements, what astronomers call metals, have been accumulating within their home galaxies, enriching the gas from which new stars and planets will form. But a galaxy is a closed system, hoarding its precious resources. Then, a cluster merger arrives. The immense forces we have discussed, the ram pressure stripping, and the powerful galactic winds driven by starbursts, act as a cosmic blender. They violently churn the galaxies and rip out their enriched gas. This process does something profound. It ejects these heavy elements from their galactic cradles and flings them out into the vast intracluster medium. The hot plasma that fills the space between galaxies becomes polluted, seeded with the ashes of countless stellar furnaces. Iron, oxygen, silicon, and neon are now suspended in a million-degree cloud that stretches for millions of light years. This act of cosmic recycling is essential. Without it, the elements necessary for rocky planets, for oceans, and for life itself would remain locked away inside individual galaxies. The violent merger scatters them like seeds across the entire cluster ecosystem. When this enriched gas eventually cools, perhaps in the far future to form new stars in a different galaxy, those stars will be born from material already rich in heavy elements. They will have a much higher chance of forming complex planetary systems. In this way, a catastrophic collision acts as a master chemist, stirring the primordial pot and ensuring that the building blocks of complexity and potentially life are available not just in one place, but throughout an entire metropolis of stars. But how can we read this history written in fire and gravity? Astronomers have learned to classify galaxy clusters into two fundamental states, labels that tell the story of their recent past. These are relaxed clusters and disturbed clusters. A relaxed cluster is the picture of cosmic serenity. In X-ray observations, it appears as a beautifully smooth, spherical, and symmetrical glow, like a perfect, luminous pearl suspended in the dark. The hot gas is concentrated at the center, gradually fading out toward the edges in a predictable, calm profile. At the very heart sits a single, dominant brightest cluster galaxy, often with a supermassive black hole that is gently humming, not screaming. This symmetry is the key. It tells us that this cluster has been left undisturbed, perhaps for many billions of years. Gravity has had ample time to smooth out any wrinkles, to settle the gas and galaxies into a state of equilibrium, a quiet retirement after a turbulent youth. The Coma cluster, a vast collection of thousands of galaxies, is a classic example of a relaxed system, its hot gas forming a placid, almost featureless pool. On the other hand, a disturbed cluster is a portrait of cosmic chaos. This is a system caught in the act of a major merger, or still reeling from one. Its X-ray image is anything but smooth. It is asymmetrical, lopsided, and full of dramatic structures. You will see the sharp edges of shock fronts and cold fronts, where different layers of gas are slamming together or sliding past one another. You can spot multiple clumps of bright gas, the remnants of the cores of the original clusters that have not yet coalesced. The galaxies within it will not show a neat, central concentration, but will appear as two distinct swarms still intermingling. The bullet cluster is, of course, the textbook example of a disturbed, merging system. Every jagged feature, every tear in its X-ray glow, is a chapter in an ongoing story of collision. This simple classification, relaxed versus disturbed, is not just a label. It is the first, crucial step in an archaeological dig. By looking at a cluster's shape, we can immediately infer its dynamical history, asking the most fundamental question: has this cosmic city known peace, or is it still echoing with the violence of a recent, world-shattering impact? Beyond the shock waves, a different kind of boundary carves through the wreckage. In the X-ray glow of a disturbed cluster, astronomers sometimes spot something that seems to defy physics, a razor-sharp edge, as if drawn with a cosmic ruler. This is a cold front, and its name is a deliberate paradox. We are not talking about something cold in an earthly sense. The gas on the so-called cold side is still blisteringly hot, often around 50 million degrees. The key is that it is significantly colder and denser than the gas on the other side of the boundary, which might be a raging 100 million degrees. This sharp divide marks where a surviving core of dense gas from one of the original clusters is plowing through the hotter, more diffuse gas of the merger. Imagine a dense, heavy blob of oil moving through a thinner, hotter liquid. The two fluids have different densities and temperatures, but they do not instantly mix. That is precisely what we see. A cold front is not a shock wave, which is a supersonic compression. It is what physicists call a contact discontinuity, a boundary where two different materials simply touch. It is the cosmic equivalent of a weather front on Earth, where a mass of cold air meets a mass of warm air, creating a distinct line in the sky. The astonishing part is how incredibly thin and well-defined these cosmic fronts remain. In a chaotic, turbulent environment where everything should be churned together, these edges stay sharp for millions of years. This tells us something crucial about the invisible forces at play. The hot intracluster medium is threaded with magnetic fields. These fields, though weak by earthly standards, act like a cage. They wrap around the colder, denser gas blob, suppressing turbulence and preventing it from dissolving into the hotter surroundings. The sharpness of a cold front is therefore a direct measurement, a ghostly imprint of the magnetic fields that structure the plasma sea. So while shock waves show us the violence of the impact, cold fronts reveal the surprising order preserved within the chaos, a delicate structure maintained by forces we cannot see. This sharpness in the chaos is a clue, but the cluster's true power over light is far more dramatic. The immense mass of a galaxy cluster, a tapestry woven from galaxies, hot gas, and dark matter, does something profound to the very fabric of the universe around it. It warps space-time. According to Einstein's theory of general relativity, mass causes space to curve, and light must follow those curves. A single galaxy creates a small dimple in space-time, but an entire cluster, especially one distorted by a merger, creates a deep, complex well. This transforms the cluster into a natural telescope, a gravitational lens of staggering power. When the light from a distant galaxy, far behind the cluster, travels toward us, it passes through this warped region. The paths of the light rays are bent like light passing through a lumpy piece of glass. The effects are breathtaking and come in two forms. Weak lensing causes a subtle, statistical stretching of the shapes of thousands of background galaxies, allowing us to map the cluster's total mass, as we discussed with dark matter. But strong lensing is the spectacular show. It occurs near the cluster's densest cores, where the curvature of space is most extreme. Here, the distortion is not subtle, it is transformative. The light from a single background galaxy can be bent into multiple paths, creating several distinct, magnified images of the same object around the cluster's edge. Even more stunningly, if the alignment is perfect, the galaxy's light can be stretched into long, luminous arcs, like celestial smiles etched across the sky. These Einstein rings and giant arcs are not physical structures, they are optical illusions on a cosmic scale, mirages created by gravity itself. For astronomers, this is a gift of immense value. First, it acts as a natural magnifying glass. The lensing effect can amplify the light of a distant, faint galaxy by 10, 20, even 50 times or more. This allows our telescopes to peer far deeper into the early universe than they ever could alone, spotting infant galaxies from the cosmos's first billion years. Second, the pattern of the arcs and multiple images is a precise blueprint. By reverse engineering how the light was bent to create that specific pattern, scientists can map the distribution of mass within the cluster with exquisite detail, tracing the invisible dark matter skeleton that holds the entire lens together. In a merging cluster, where the dark matter has been separated from the gas, this lensing map becomes the definitive proof, the ultimate witness to the ghostly nature of most of the universe's substance. These cosmic mirages are windows not just into mass, but into time itself. The most distant mergers we can detect are not merely far away, they are messages from the universe's youth, sent when it was a fraction of its current age. Astronomers refer to this distance as high redshift, a stretching of light's wavelength that tells us an object is rushing away from us due to the expansion of space. A high redshift merger is a collision we are witnessing from a time when the cosmos was denser, hotter, and far more chaotic. Why is finding these ancient smash-ups so crucial? Because they are the formative events, the construction sites where the first giant clusters were being assembled from smaller building blocks. In the present-day universe, we see majestic, relaxed clusters, the finished products. But to understand how they were built, we need to catch the builders at work. Observing mergers from when the universe was, say, 3 or 4 billion years old allows us to test our fundamental theories of cosmic structure formation. Did dark matter behave the same way back then, separating cleanly from gas in those primordial collisions? Did clusters grow primarily through these violent mergers, or through a steadier trickle of matter along filaments? The answers are written in the X-ray glow and gravitational lensing patterns of these ancient systems. Each one is a benchmark, a snapshot of the universe at a specific, younger age, allowing us to create a flipbook of cosmic evolution. Pushing these observations to greater distances, to higher redshifts, is one of the great frontiers of modern astronomy. It requires the combined power of our most advanced observatories. The Chandra X-ray Observatory peers through the inferno to map the hot gas in these early collisions, while the James Webb Space Telescope, with its infrared eyes, cuts through dust and looks back to see the infant galaxies caught in the act of merging. By comparing these ancient events to the bullet cluster in our cosmic backyard, we can see if the rules of physics played out the same way in the early, more energetic universe. Every distant merger discovered is another piece of the puzzle, telling us how the grand cities of the cosmos were forged in the fires of the dawn time. That diffuse radio whisper we detect is not always a sharp, distant arc. Sometimes it takes the form of a vast, ghostly cloud that seems to swallow the entire heart of the wreckage. These are radio halos, and they are among the most puzzling signatures a merging cluster can leave behind. While a radio relic traces a single, powerful shock wave on the outskirts, a radio halo is something else entirely. It is a roughly spherical, incredibly diffuse region of radio emission that fills the central volume of a disturbed cluster, coinciding with the turbulent, hot gas seen in X-rays. Its glow is not concentrated, but smeared across millions of light years, a faint, crackling fog that permeates the core. The mystery lies in its origin. The electrons producing this radio light are incredibly energetic, but they cannot have traveled far from where they were accelerated. Otherwise, their signal would smear into invisibility. This means something must be re-energizing particles right there in the chaotic central soup. The leading theory points to the immense turbulence stirred up by the merger. As the cluster cores swing past each other and finally coalesce, they churn the magnetized plasma like a cosmic spoon in a pot. This turbulence creates a web of second-order shock waves and waves in the magnetic fields themselves. These phenomena can give old, slower-moving electrons a fresh kick, re-accelerating them back to the relativistic speeds needed to produce the radio glow we see. It is a continuous, chaotic re-energizing process happening throughout the entire core. For astronomers, the presence of a giant radio halo is a clear and powerful signpost. It announces, with certainty, that this cluster has experienced a major merger, likely within the last billion years or so. That faint, spherical static is the lingering echo of the violence, a testament to the energy still sloshing through the system long after the most dramatic collisions have passed. The faint radio halo is a clue, but to truly decode the chaos, we need to run the experiment ourselves. Since we cannot witness a single merger from start to finish, we must build a universe inside a machine. This is the realm of cosmological simulations, where the world's most powerful supercomputers become time machines for the cosmos. Projects with names like Illustris, TNG, and the 300 Project are the digital laboratories where our theories are tested. Physicists begin with the fundamental laws of the universe, the equations of gravity, gas dynamics, and the peculiar rules of dark matter. They define a vast volume of virtual space, seed it with tiny density fluctuations from the early universe, and press play. The computer then calculates the gravitational dance of trillions of particles, representing dark matter and ordinary matter, as they evolve over billions of simulated years. Galaxies form, clusters grow, and inevitably, these titanic structures are drawn together. In this virtual cosmos, we are not limited to a single, frozen snapshot. We can watch the entire collision unfold from every angle. We can rewind to see what the clusters looked like before they ever met, and fast forward to see their final, relaxed form eons from now. This power is transformative. When we look at a real object like the bullet cluster, we see a single moment, but by running thousands of simulations with slightly different starting conditions, speeds, and angles of impact, we can find the digital collision that best matches our real-world observation. That matching simulation becomes our guide. It tells us precisely what stage of the merger we are witnessing, what happened 100 million years before the image was taken, and what will happen next. It reveals the invisible connections, showing how the shock wave we see today was launched, and where the dark matter clumps will drift. Without these digital universes, our snapshots of cosmic violence would remain beautiful but bewildering mysteries. The simulations provide the narrative, the storyboard that turns a single, spectacular frame into an epic film of creation and destruction. That dormant monster at the center of the brightest cluster galaxy is often sleeping, but a merger is the perfect alarm clock. The gravitational turmoil of a collision does far more than just stir the hot gas between galaxies. It violently shakes the galaxies themselves. Within a galaxy, vast reservoirs of cold gas that were orbiting peacefully can be suddenly thrown off their stable paths. The chaotic gravitational tides from the passing clusters can torque these gas clouds, sending them spiraling inward on a one-way trip toward the supermassive black hole lurking at the galactic core. Think of it like tilting a bowl of water. The liquid that was content to sit at the edges suddenly rushes toward the lowest point. For the brightest cluster galaxy, sitting at the gravitational bottom of the entire system, this effect is magnified. A colossal influx of new fuel, gas that had been minding its own business for billions of years, is now dumped directly onto the black hole's doorstep. This is the cosmic equivalent of throwing gasoline on smoldering embers. The black hole awakens with a vengeance, beginning a frenzied feast. As matter spirals into the accretion disk, it is heated to millions of degrees by friction, glowing brilliantly across the electromagnetic spectrum. But the black hole is a messy eater. Not all the incoming material crosses the event horizon. Some of it gets channeled by powerful magnetic fields into twin, focused beams of energy and matter that scream outward from the poles at nearly the speed of light. These are the relativistic jets we mentioned in the feedback loop, and when switched on by a merger, they can become truly monstrous. They punch through their host galaxy and extend far out into the intracluster medium, inflating gigantic, bubble-like cavities in the hot gas that can be hundreds of thousands of light-years across. This sudden eruption of an active galactic nucleus, or AN, is a transformative event for the entire cluster. The jets pump tremendous energy back into the surrounding gas, reheating it and preventing it from cooling and forming new stars. This is the feedback loop in its most dramatic phase, a self-regulating mechanism where the black hole's own feast ultimately shuts off its future food supply. A major cluster collision can thus trigger a brilliant, violent outburst that dictates the thermal fate of the core for the next billion years, proving that the true heart of a cosmic city is often a sleeping dragon, waiting for a quake to wake it. These jets and shock waves are factories for particles of almost inconceivable power, but their ultimate product is even more extreme. Colliding galaxy clusters are now suspected to be the source of the highest energy photons in the entire universe. We have crossed from the deep hum of radio into the searing flash of gamma rays, the most energetic form of light on the electromagnetic spectrum. The process begins with those ultra-relativistic particles, the protons and electrons accelerated to near light speed by the merger's shock waves. These particles do not travel in a perfect vacuum. They are bathed in an ancient, faint glow that fills all of space, the cosmic microwave background radiation, the afterglow of the Big Bang itself. When a proton, hurtling at nearly the speed of light, collides head-on with one of these low-energy background photons, something extraordinary happens. The impact is so violent, it can transform the interaction, producing new particles, including neutral pions that almost instantly decay into a pair of gamma-ray photons. These are not ordinary gamma rays. They carry a staggering amount of energy, measured in teraelectronvolts. 1 teraelectronvolt is a trillion times the energy of a photon of visible light. To put that in human terms, it is roughly the kinetic energy of a flying mosquito, but packed into a single subatomic particle of light. These are the universe's most powerful bullets of pure energy, and merging clusters are some of the prime suspects for their origin. The turbulent environments and immense shock fronts provide the perfect accelerators to create the particles that then spark these photon-generating collisions. Observatories designed to detect these fleeting, ultra-high-energy gamma rays, like the upcoming Cherenkov Telescope Array, are now pointing their instruments at known merging clusters. They are hunting for the faint, telltale flashes of Cherenkov radiation these gamma rays create when they strike Earth's atmosphere. Each potential detection is a clue, a signature that we are pinpointing the cosmic engines capable of forging light at the very edge of what the laws of physics allow. Deep in the southern sky, a distant titan earns its nickname. The El Gordo cluster, officially catalogued as a CT-CLJ0102-4915, is Spanish for the Fat One, and it is a title well deserved. This is not a merger in our cosmic backyard, but a colossal collision we are witnessing from a time when the universe was roughly half its current age. Yet despite that vast distance, El Gordo shines with a ferocious intensity. It is one of the most massive, the hottest, and the brightest X-ray clusters ever discovered at such a great look-back time. Its sheer scale is staggering, with a total mass estimated to be around 3 quadrillion times that of our Sun. The temperature of its seething intracluster gas soars to a blistering 200 million degrees Celsius, far hotter than the core of our Sun. This extreme heat makes it blaze in X-rays, a beacon of violence across billions of light years. But El Gordo is more than just a record holder. It is a profound cosmological puzzle. According to our best models of how structure forms in the universe, such an immense, fully assembled cluster should not exist that early in cosmic history. It is like finding a skyscraper in the ruins of an ancient city where archaeologists expected only small huts. The existence of this behemoth so early challenges some simulations of cosmic evolution, suggesting that these giant structures may have been able to form and collide faster than we thought possible. This makes El Gordo a stringent laboratory for our theories. Its properties, the speed of its merging components, the distribution of its dark matter mapped through gravitational lensing, and the sheer energy of its X-ray glow, all put immense pressure on our understanding of dark matter's behavior and the timeline of cosmic assembly. Every observation of this distant, fat cluster is a test, forcing us to refine our picture of how the universe built its greatest cities in the frantic rush of its youth. The invisible architecture of a cluster is woven from more than just gravity. That superheated plasma filling the void is not a simple gas, it is a magnetized fluid, threaded with vast, tenuous magnetic fields. These fields are incredibly weak by earthly standards, millions of times fainter than a common refrigerator magnet, but they are unimaginably large in scale, stretching for hundreds of thousands of light years. In the calm of a relaxed cluster, these fields may lie in quiet, orderly loops, but when two clusters collide, this magnetic tapestry is thrown into chaos. The turbulent motions, the sloshing and churning of the multimillion-degree plasma act like a cosmic mixer. They grab these immense, invisible lines of magnetic force and stretch them, twist them, and tangle them into a frenzied knot. This process, called turbulent dynamo action, does something remarkable. It actually amplifies the magnetic fields, making them stronger within the turbulent wreckage. You can picture it like stirring a cup of coffee with a spoon. If you drop a few drops of food coloring into the cup, the gentle stirring at first just stretches the color into thin strands. But if you stir violently and chaotically, those strands become wildly twisted and folded, spreading the color throughout the entire fluid in a complex web. That is what happens to the magnetic fields in a merger. This amplified magnetism is not just a curious side effect, it is a fundamental player in the aftermath. Those ultra-energetic cosmic rays, the particles accelerated to near light speed, are charged. They cannot travel in straight lines through a magnetized environment. Instead, they are forced to spiral along the twisted magnetic field lines. This confinement is what traps them in the cluster, preventing them from simply escaping into the void, and it is this spiraling motion that generates the faint radio whisper we call synchrotron radiation. The beautiful, sharp arcs of radio relics and the diffuse clouds of radio halos are direct maps of this amplified, tangled magnetism. We are not just seeing particles, we are seeing the ghostly imprint of magnetic fields stretched across the cosmos by violence, a force field woven from chaos itself. That invisible magnetic web can sometimes paint a picture so clear it earns a nickname from our own world. Meet 1 RxSJ0603.3 plus 4214, a distant galaxy cluster known to astronomers by a far more memorable title, the Toothbrush Cluster. The reason is instantly visible in radio wave images. Stamped across the sky is a colossal, nearly perfectly straight line of radio emission, over 6 million light-years long, with a fainter, diffuse brush-like region at one end. The resemblance to a giant, cosmic toothbrush is uncanny. This bizarre, linear structure is a radio relic, but it defies the typical expectations. Most relics are curved, tracing the arc of a spherical shock wave expanding outward. The toothbrush's relic is strikingly straight, a clean, sharp line etched into the fabric of the cluster. This unique morphology is a direct challenge to our models. It suggests the shock wave that created it was not a simple, expanding sphere, but something far more planar and focused, perhaps a vast, nearly flat sheet of energy propagating through the magnetized plasma. Even more intriguing, this linear relic is not isolated. It appears connected by faint radio bridges to other diffuse emission in the cluster, hinting at a complex network of particle acceleration and magnetic field connections woven throughout the entire merger site. The Toothbrush Cluster has become a prime cosmic laboratory. Its strange, clean lines force physicists to refine their simulations, to ask how such a perfectly straight shock could form and persist. It pushes us to understand how energy is channeled and particles are accelerated across these immense, interconnected systems. This isn't just a curious shape, it's a question written in radio light, demanding we rethink the intricate physics of how violence propagates through the universe's largest structures. These immense collisions are more than astronomical events. They are windows into the most fundamental behavior of matter itself, the superheated, magnetized plasma that fills a merging cluster is a state of matter we simply cannot recreate in any laboratory on Earth. In our labs, we can contain tiny, fleeting amounts of plasma for fractions of a second under immense pressure, but in the cosmic arena, nature provides a laboratory of staggering scale, where plasma exists in a diffuse, magnetized state for billions of years, shaped by gravity and stirred by unimaginable violence. By observing how this plasma behaves during a cluster collision, we are learning the universal rules that govern this fourth state of matter, rules that apply far beyond this single, spectacular context. Every shock wave we map is a lesson in how energy propagates through a thin, magnetized medium. The turbulent sloshing of the gas teaches us how chaos transfers energy across vast distances and amplifies magnetic fields. The ghostly radio halos and relics are direct experiments in how particles are accelerated to near light speeds by these natural processes. This knowledge is not locked away in the cosmos. It is profoundly relevant. The same physics that creates a million light-year-long shock front in a cluster is at work in the solar flares that erupt from our own sun, capable of disrupting satellites and power grids. It governs the behavior of the plasma that fills the space between stars in our own galaxy, influencing how stars are born. Perhaps most compellingly, understanding how to confine and control hot, turbulent plasma is the central challenge in humanity's quest to harness fusion energy, the process that powers the stars. By studying the universe's largest and most violent plasma experiments, we gain insights that could one day help us build a clean, limitless energy source here at home. The dance of colliding clusters is, in the end, a masterclass in the physics that shapes not just galaxies, but the very fabric of our technological future. Our own cosmic neighborhood is quietly following the same script written by gravity. The Milky Way and Andromeda, the two titans of our local group, are already on an inescapable collision course. In about 4 billion years, they will begin a slow, majestic dance that will end with their merger into a single, colossal elliptical galaxy, a future astronomers have nicknamed Milkomda. This will be a spectacular, slow-motion replay of the galactic mergers we see within distant clusters, but it is only the first act of a much grander story. For our local group is not an island. We are a small, outlying suburb of a true cosmic metropolis, the Virgo cluster, a gathering of over 1,000 galaxies centered about 54 million light-years away. And just as individual galaxies are pulled together by gravity, so too are galaxy clusters. The entire local group, with Milkomda at its heart, is already falling toward the immense gravitational pull of the Virgo cluster. This journey will take tens of billions of years, an almost incomprehensible span of time, but the destination is clear. Eventually, our merged home galaxy and its few remaining satellite companions will plunge into the outskirts of that vast cluster. We will cease to be a quiet, isolated group and become citizens of a roaring galactic city. And in the even more distant future, beyond any timescale we can truly grasp, the Virgo cluster itself will likely experience its own epochal merger, perhaps with another giant like the Coma cluster. Any civilization that endures in that era, orbiting a star forged from the ashes of the Milky Way and Andromeda, would have a front-row seat to the ultimate cosmic spectacle. They would witness from within the very processes we have spent this journey exploring. They would see galaxies whipped into new orbits by gravitational tides, watch shock waves heat gas to hundreds of millions of degrees, and detect the ghostly separation of dark matter from the visible wreckage. The great cycle of construction and destruction that built the universe would, for them, become a local event. Our story, and the story of every star and planet we know, is ultimately a prelude to that final, magnificent collision, a single thread being woven into the largest tapestry the universe can make. These titanic collisions are the universe's grandest experiments, unfolding on scales of space and time that defy human intuition. They last longer than our planet has existed, reshaping entire cosmic metropolises over billions of years. Yet within their slow-motion violence, they act as perfect detectives, revealing the ghostly presence of dark matter by showing us where most of the mass is not. They forge environments of extreme physics, heating gas to hundreds of millions of degrees and accelerating particles to energies we can never hope to replicate. And they are not random acts of destruction, but essential chapters in the story of cosmic evolution, building the largest structures we know, seeding future galaxies with the elements for life, and testing the very laws that govern our reality. By studying these collisions, we are not just watching a distant spectacle, we are answering the most fundamental questions about what the universe is made of and how it came to be the vast, structured tapestry we see today. In a cosmos defined by such perpetual, majestic violence, our own peaceful corner of space feels both precious and temporary. We are living in the quiet prologue before our own galaxy joins the dance. So tell us, which of these 30 facts reshaped your understanding of the cosmos the most? Was it the ghostly proof of dark matter, the deep hum of the Perseus cluster, or the future collision of our own Milky Way? Let us know in the comments below, and if you enjoyed this journey through the deepest space mysteries, subscribe to stay curious with us.